afternoon, everyone. Welcome to attend AEIC conference. I'm Winnie, today's host. It is honor and pleasure to have you attending this online conference. The conference is to held every year to make it an ideal platform for people to share views and experience in the field of education, knowledge, and information management and related areas. I would like to extend our warm welcome to all of you. The conference is scheduled to end at around 6 p.m., including 3 keynote speakers and 10 oral speeches. After each speech, there will be discussion time. If you have any question, please raise the question with the icon, raise hand, or leave a message in group chat. Thank you. After the first speech, there will be a group section. We will capture a screen for all the participants. Thank you for your cooperation. Now, let's welcome the first keynote speaker, Professor Thomas Canhao Xu, BNU HKBU United International College, China, to make the keynote speech. The title of his speech is Hardware Co-Design of Efficient Deep Learning Algorithm. Let's welcome.
Okay, so hello everyone.
Hello.
Can you hear me?
Yes.
Okay,
please
good.
Go on.
So yes, let me share my screen. So let me check. I should share my screen from here, I think. I think it's from here. No, it's from desktop 1, I think.
Oh,
Let's see.
Okay, I can see your screen now.
So you can see my screen, can you?
Yes, yes.
So it's full screen, right?
Yeah, it is in full screen now.
Okay, that's good. All right, thank you very much. Thank you. So as you know, I'm Thomas. So I'm from the Beijing Normal University, Hong Kong Baptist University, United International College. So this is in Zhuhai. So we have a joint college for this education purpose in Zhuhai. So this, let's say, college is started like 15 years ago. So only a few 2 months ago, I think last month, we celebrated our 15-year anniversary, let's say, in Zhuhai. So it's a long time. And today my topic is about the hardware software co-design of the efficient deep learning algorithms. So yeah, so basically, well, I want to talk something about myself. So, well, as you know, I'm Thomas, so Chinese name, Xu Canhao, right? So I got my Master of Engineering in 2007 from Zhejiang University. And I got my PhD degree in the University of Turku in Finland, 2012. So it's 8 years ago. And I worked in the University of Turku in Finland, and I worked in Suzhou University in China, and then UIC. So starting from 2006. So as you know, this year, 2021, it's already 15 years. And yeah, I worked in Finland and Germany for about 10 years in European countries. So, and I started my teaching since 2006. So I taught about 20 courses in different areas. And I've my researching since 2008 when I start my PhD research in Finland. So published like more than 80 papers and projects from academics and the industry, over 15. So, well, and of course, a lot of international collaboration, and I was interviewed by some international and national media. So that's in general about me. And of course, you can, if you are interested, you can, of course, find a lot of information about me by putting my name in, for example, in Google. So if you put my English name in Google, you can find some results, like from the Google Scholar and from different places. So, wow, you can find some information. And also you can find some information from Baidu, I think. So if you put my Chinese name, as I said, I'm my Chinese name. If you put it in Baidu, you can find some information as well, like from the Suzhou University and from here and there. And you can find my interview from different media, like the Tencent and from People Daily and from here and there. So yeah, you can find some information about me. So, well, you can know me better, all right? But anyways, I'm currently working in UIC, as you know, and I also hold several other positions, but that's about it. And my main research, as you can see from my interview and my research here and there, are artificial intelligence and, of course, the 5G and these kind of things. So, well, that's the thing we are going to talk about for today, all right? So, of course, one thing is that why we like to talk about the deep learning and machine learning in general for today, for these days, because it's very hot. And it's not only the deep learning, but also we have another topic. So if you take a look at the conference this year, this is the conference called the ICLR, or let's say this is the International Conference for Learning Representatives. So it's for the machine learning and deep learning, and of course reinforcement learning. So a lot of learning stuff in this machine learning stuff in this conference. So as you know, if we take a look at the conference topic, we know that most of people are interested in this deep learning and reinforcement learning. So wow, this is the trend, at least for nowadays. So this is for the research. And if you take a look at the top 50 keywords for the papers submitted to the conference, you know that basically the deep and reinforcement learning are quite hot these days. Well, it's not only hot these days, but it's been there for quite a long time. It's been there for several years for the deep learning. Well, I think the first time anyone heard about this, most people, I mean the general public, heard about this topic, the deep learning or the machine learning. It started like 5 years ago. So 5 years ago, I think you heard about this AlphaGo, right? You heard about this AlphaGo. So this AlphaGo is about playing the Go game, of course. That's the name come from. In 2015 and 16, we have the AlphaGo beating the 9 Dan best Go players, human Go players. So, well, this is the very good first real concrete work for machine learning and deep learning. So in fact, it's not that complicated nowadays because it's already 5-6 years ago. So we know that the algorithm is based on the deep convolutional neural network, or let's say the DCNN. In fact, later on, they have improved their algorithm based on the ResNet, or the so-called residual networks. Not only this, but they also have combined the Monte Carlo tree search, or so-called the MCTS, and the reinforcement learning. So putting all together, they have their AlphaGo, the backbone of the algorithm. So in 2016, that's the first time we know that the AlphaGo can beat the Lisador 4/4/1 without any handicap. And 2017, the so-called AlphaGo Master beats Keji with 5/1 and then the online master race for the 60/0, and later on they have this AlphaGo 0, and then they have this AlphaGo Alpha 0. So this is kind of complicated. So this happens basically in about 2 years. They published some papers in Nature and Science. So basically introduced the idea of the Go game. And I think later on they have only a few months ago. In fact, December of 2020. So last month they published this paper called Mu0. So this kind of it's the latest research for the AlphaGo team. So basically, the first AlphaGo, they have focus on the Go game, and they have the knowledge for the human data and for the domain knowledge and the rules. And later on, the Alpha 0, they don't have the human data and domain knowledge. And later with the Alpha 0, they can play even not only Go, but also chess and Shopee. So for the latest Mu0, they can even play the console games without any rules input. So this seems to be very powerful already for now. But of course, since they are always improving the this kind of algorithm, so of course we can see more. Well, we expect more in the future for their work, of course. So, of course, that's only the first step of the team for working on the machine learning or deep learning or the reinforcement learning. But in fact, they didn't stop. They move on to the so-called imperfect information games. So what's this game for? Well, as you know, the so-called goal is the perfect information game. So basically, you know all the information on board. So basically your opponent, the move, everything is transparent and you can see everything. The knowledge is there, so you can see everything. But in a lot of games, the information is hidden. So basically we call this imperfect information games. And like this StarCraft, the strategy game, the real-time strategy game, it is totally imperfect because, well, you don't know what the opponent is doing. For example, maybe the opponent is collecting the resource or building some units or building some base and moving, and there is this fog of war. So everything you don't know. You don't know a lot of things. You only know things you did. But for the things your opponent did, you don't know. So this kind of imperfect information games. And of course, it's real time. So it's more complicated than Go. For example, for Go, you have like 1 or 3 or 5 minutes per step to think about it. But for the StarCraft, you don't have that time. The only thing you have is only, well, let's say milliseconds, so you can think of it. So this kind of it's even more difficult. So, well, several years ago, some experts in artificial intelligence, they predicted that no single AI can solve the problem of, for example, the StarCraft. But as you know, a few years ago, the DeepMind, they indeed solved the problem partially for the StarCraft. So they developed an AI called the AlphaStar. So basically, they defeated the best players in the world. And their architecture, if you take a look, is based on the residual networks, the ResNet. And also they have the transformer and the long short-term memory, or the LSTM. And also they have a lot of other things in the architecture. So based on this neural network, the architecture, they can defeat, at least they have demonstrated they can defeat the best human players. So this is another of their work by the DeepMind. And of course, what they have been doing recently is the protein folding. I think you heard about it, some of you. So basically, we have the protein folding problem, and we have to predict if we giving you a segment of the protein, you have to predict what kind of folding it will be. And this is a very tricky problem. And in fact, there's no good way of predicting this kind of protein structure. So, well, recently they have proposed this AlphaFold. So with the second generation of the AlphaFold, they can basically achieve nearly 90% of the accuracy. So, well, we only know the announcement that they can do it, but we don't yet know the details. So they didn't publish the paper, the details yet. So, well, I think recently, maybe within a few months, they will publish it. So we'll see. And a lot of scientists and experts say that this could be one of the Nobel Prize winner. Well, we'll see, because this is kind of a very competitive scientific results, all right? So AlphaFold. And of course, besides these kind of big things, we also have the, I think in recent months, we also heard about this NLP for the natural language processing. So just 6 months ago, in June 2020, we have the GPT-3, so-called the generative pre-trained transformers. So they have produced a very smart, the natural language processing robot. So basically it can talk with you. So natural language talking, much smarter than the, for example, 小爱同学. So, but this kind of system is very complicated, and it's trained, for example, with 175 billion parameters. So this kind of super huge system. So, well, these are the recent research results for, as you know, for the machine learning and deep learning and these kind of things. But there are problems for this kind of research, as you know. So for example, well, if you want to develop something for machine learning and deep learning, of course, we have to use some kind of framework. So for example, what we use, for example, most of the time, maybe we use the Keras based on the TensorFlow, of course, or from time to time, maybe we can use the MXNet, or maybe you like the PyTorch or something else. So, well, these are the machine learning and deep learning frameworks you use. So this is a common thing. So, but this is only the software. On the other hand, you also have the hardware. So you have the code and the algorithm, and you have to deploy those things to the hardware. And in this case, of course, you have the CPU, you have the GPU, or you have the NPU, the neural processing unit, or maybe the FPGA. And for now, at least, we need a lot of hardware to process everything. So for example, in the case of AlphaGo, we have a huge amount of hardware requirement. So as you can see here, in the case of the earlier version of the AlphaGo, they used like thousands of CPUs. So in this distributed version of AlphaGo, they have 1,920 CPUs, and they have used 280 GPUs in this case to reach this Elo rating of 3,168. So this requires huge amount of hardware processors. And you know, it's only possible for companies like Google like super big companies, but it's very difficult for like a university because we don't have that much resource. And of course, for companies like Google, they have the resource, they have the money, so they can even develop, they can even design their own processing unit. So as you know that they found that the GPU and CPU are pretty slow, so they even developed their own processor, so-called the TPU, and this is called the tensor processing unit. So well, they have like 65,000 units, and it's even faster than the GPU. So wow, this is something they have. So as you know, you need a lot of hardware support for the algorithm. So that's a tricky issue. That's a tricky issue. So think about it. If you want something to work, we can't have like hundreds of thousands of processors in your system. This is only something you cannot do. So think about it. If you want to make it work, really, if you want to make it work, then of course you have to think about how to process these kind of things. How to process these kind of things. And for example, you have to think about do you process things locally, or are you, for example, transferring this kind of information to the server, to online, or do you want to do hybrid processing? So for example, if you are doing the local processing, of course, the data are collected and processed locally. For example, in some cases, this is totally inevitable. So think about it in this kind of autonomous driving, like the Tesla cars. So of course, the data must be processed locally. We can't say that I'm uploading my pictures and videos to the cloud and wait for some time for processing and then I have the results. That's impossible for the autonomous driving. And also for industry, for military, for aerospace. So for this kind of systems, for this kind of applications, this is basically inevitable. So you have to collect and process data locally. So on your system. This is something you have to do. And of course, most of the time for what we do now, like if we do some coursework or some kind of paper research, well, of course, we can do online. That's for sure. We use the platform. For example, we have a GPU server, or we have a, for example, the Google Colab, or we have the Kaggle. They have some free GPU resources we can use. We wait for a few hours and we get the results. That's okay, because that's totally fine, only for experiment. And of course, from time to time, you can use the hybrid. But as you know, if you want to make it work, I think the local processing is something you cannot avoid. So for example, if you take a look at this video, if you take a look at this video sequence, you can find that this video is the video from the Tesla autonomous driving. All right, this is from the Tesla autonomous driving. So basically, you can see this is the camera from the onboard computer. So from the Tesla car. And those lines, those marks, and those numbers are the result from the Tesla, let's say, autonomous driving system. So as you can see, they can recognize the lanes, the road, and the direction marks, and the traffic signs, and different cars parked next to you. So they can recognize a lot of things. So in this case, you can have the so-called autonomous driving. As you know, this must be happened in real time. It must happen in real time. So while the processing, let's say, delay can only be something like a few milliseconds. So we have to achieve like at least 30 frames per second, or maybe we require 60 frames per second, something like that. So this kind of system is some system you can use, right? It's some system you can use. So that's what we are calling. If you want to really use the system in real world, you have to think about this, the so-called hardware, software, co-design. So unless you just want to leave it to the lab, to the course, otherwise you have to make something work. If you want to make something work, you have to think about the hardware, software, co-design. So of course, the Tesla system, the autonomous driving Tesla system is based on some kind of hardware. And in fact, Tesla knows that they can't get some hardware like from the NVIDIA GPU, they can't get it to achieve such kind of performance and accuracy. So as we know, for them, they have developed the own silicon. So this is the latest Tesla hardware for processing their AI, machine learning, deep learning algorithms. So as you can see on your right hand, this is the silicon. So basically the chip, they manufactured their own chip, all right? They didn't use any chips from Intel or from NVIDIA. They didn't use these kind of chips. Instead, they developed their own chips, all right? They have their own chip designing team, and they have their own chip software and hardware architecture. So programmers and the whole software stack, they have their own team, all right? So as you can see, the board on your left hand, it is the Tesla onboard computer, all right? So if you have a Tesla car, and you can easily find this kind of board. It's a computer inside your Tesla car. So this is the computer processing the autonomous driving algorithm. So as you know, this is something you must have, right? If you want it really happen, okay? And of course, this is not very practical for everyone because, well, I think most of the people cannot afford to buy a Tesla car. It's still quite expensive, but iPhone may be cheaper. So you can find a pretty powerful processor in your iPhone. For example, it's only a few thousands of Chinese yuan, so you can get an A14 processor. So in this case, in the A14 processor, you already have a 16-core neural engine. So this is basically a machine learning processor, all right? So called the neural engine. So they can enhance your processing speed of the machine learning or the matrix multiplication operations. So what's the performance here? As you can see, they can achieve like 11 trillion operations per second for the mobile processor. So this A14 SoC is really powerful for the system, all right? For your phone. Only with your iPhone you can get such kind of speed. So well, you can see that basically nowadays, if you want to make some product, make it really happen. So you want to make something concrete, then you will need hardware support for the algorithm. So that's what we did in recent years. So for example, we have several publications in recent years. For example, we have most of our research are focused on the image detection part. So like the segmentation of the pictures. So for example, we have a few years ago, we have the segmentation on the lung contour and of course the chest radiographs by using some kind of method in machine learning and these kind of things. And also we have the deep learning stuff. We have the deep learning and, for example, the deep belief network and the hybrid method to increase the speed. You know that on one hand, of course, you can always increase the accuracy, but of course, if you sacrifice the time, if the time you spend on some algorithm is like tens of hours, then we think that this is not very good. We prefer to have a very efficient algorithm. So, for example, in our algorithm, the speed, for example, is like hundreds of times faster, but we only sacrifice a little bit of the accuracy. So only like few percent or even less than 1% of the accuracy. So that's the research we have, and also we also get some funding from the academics. So for example, we have the one funding starting from 2020 July to 2020 for 3 years from last year, and this one is image segmentation and classification for the long image based on the deep learning. And so this is one of the general funding from the Natural Science Foundation. And the other one is a software co-design for efficient machine learning algorithms. It's a startup fund from, as you know, from our UIC. So basically these projects are 3 years, so wow, from the academics. And this is only some programs from the academics, but also we have some research funding from the industry. So we are building some robot, but those are kinds of confidential, so I cannot share too much information with you. But what I can share with you is that we are doing the embedded systems and these kind of robots, all right? Not this kind of large level, like this kind of industrial robot, but kind of a smaller scale, right? So, but as you know, these kind of robots are very, how to say, very in the future, of course, in a few years. Well, for example, fighting the coronavirus, of course, using these kind of robots, you don't have to send people there, right? Because people get the virus, but the robots, they can't get the coronavirus. So it's very convincing for the future. And I think it's a very trending topic for the future. And of course, for the robot to take care of the patient with the coronavirus, that's very good, right? You don't get the virus because it's a robot. So they only get computer virus. They can't get the coronavirus, right? So this is a very trending topic in the few years. But as you know, to make it happen, we have to think about how we can implement this kind of hardware and software co-design. So we have to make the algorithm running on the embedded systems in the controllers, in the processors, in this kind of robots, instead of the huge GPU servers. So that's what we want to do, right? So basically, if you put everything together, you know what's the thing here. If you want to make a usable machine learning or deep learning algorithm, if you want to make a ubiquitous machine learning and deep learning algorithm, you have to think about these topics. So not only the machine learning, but also you have to think about what kind of platform you want to run your algorithm, like what kind of embedded devices you have, all right? For example, you have an ARM device, you have a very limited processor. So what kind of the processing power you have for the hardware? So what you can do with the limited hardware resources. So in this case, you have to think about the not only the algorithm, the accuracy, but you have to think about the so-called the software and hardware co-design. So put everything together. You have a usable, you have a ubiquitous the machine learning and deep learning. So that's what I think we'll have to think about, we have to do in the future. So that's about my speech. That's about my topic. If you have any questions, you can always send me email or anything that you can do. All right. Thank you very much. Any questions?
Thank you, Professor Thomas. Is there any question? You may raise your hand with the icon raise hand. Okay, if you guys have any question, please feel free to contact him by email. I'm sure Professor Thomas will be happy to answer it. Thank you again.
Okay, thank you very much. Thank you.
Thank you. Okay, before the second speaker, please turn on the camera. We will take the screenshot of all the participants. Thank you for your cooperation. 麻烦大家打开一下摄像头，我们将进行一个截屏的大合照。感谢大家的支持。能麻烦教授您退出一下分享屏幕吗
？Okay.
对 ，Thank you.
Okay, thank you.
好的。Yes, due to the effect of COVID-19, the conference changed to online. Thanks again, everyone, for your support. 由于疫情的原因呢，我们这次的会议改成了线上的模式。再次感谢大家的支持。Thank you. We have finished the screenshot. Thank you for your cooperation. And now, let's welcome the second keynote speaker, Professor